Hello, my name is Austin Bruce. I'm a graduate student in the Department of Neurology at the University of Iowa, where I work with Dr. Nandakumar Narayanan. The title of my talk today is going to be Modeling Interval Timing in Molecularly Defined Striatal Circuits. Let's begin with some brief background. Interval timing, the estimation of a duration on the magnitude of several seconds, is dependent upon midbrain dopamine signaling to striatal circuits. However, striatal medium spiny neurons express either the D1 excitatory dopamine receptor or the D2 inhibitory dopamine receptor. Importantly, D1 and D2 MSNs play orthogonal roles in many contexts, including movement and reinforcement learning, but their respective roles in interval timing remain poorly understood. Here, we wanted to unpack that a little. We initially hypothesized that D1 and D2 MSNs play oppositional roles in regulating temporal processing. To test our hypothesis, we trained mice on a novel interval timing task developed by Fuat Balchir, which requires discrimination between intervals of two different durations, here 6 or 18 seconds. How this task works is following initiation of a trial, mice will either be presented with short or long trials. On short trials, mice will be rewarded following the first response at a nose poke port following 6 seconds. However, in long trials, mice will be rewarded for the first response at the contralateral nose poke port after 18 seconds. Cues are identical between trials, so optimal behavior involves an initial interaction with the short latency response port after the mouse realizes 6 seconds has passed without reward, a traversal to the opposite side of the chamber, and interaction with the long latency response port. The decision to switch response ports is exclusively based on the rodent's internal representation of how much time has passed. We recorded from striatal medium spiny neurons as animals learned to perform this task, and we noted prominent ramping activity in striatal medium spiny neurons. That is, neurons which exhibited an approximately linear relationship between their firing rate and time in trial, as we can see here. This has been attested in the literature as one of the mechanisms through which striatal circuits encode time. Importantly, these can be captured very easily with generalized linear models, simply asking the question, is there a relationship between time in trial and bid firing rate? Additionally, this is a process which is amenable to being captured via drift diffusion modeling. Using this approach, we identified ramps preceding the 18-second or the 6-second targets, as we can see in this top panel here. We also included response time, that is when the animal interacted with either the short or the long latency response port as a predictor, and we found neurons that appeared to encode the motor aspects of those responses, which you can see down in panel B here. We recorded from these animals over 10 days of continued experience with this task, and we noted that both of these activity profiles increased as the animals gained experience. We were very interested in the molecular identities of the cells expressing either time-dependent ramps or motor modulation, as we saw in the previous slide. And so our first experiment to answer that question was to either systemically blockade the D2 dopamine receptor using the D2 antagonist sulpiride or the D1 dopamine receptor utilizing the antagonist SCH23390. And we found that DRD2 blockade, but not DRD1 blockade, was sufficient to attenuate this ramping process in striatal ensembles. However, interestingly, we found that D1 blockade or D2 blockade could attenuate the response modulation. This may provide a hint that the ramping process is more common amongst D2 than D1 MSNs. We followed this experiment up with optogenetic inhibition of D1 or D2 MSNs in D1 or D2 Cree mice trained to perform this task. And what we noted was that optical inhibition of D2 MSNs caused a robust delay in the times which animals were choosing to switch at. This is an effect that we didn't see in our D1 group or our control fluorophore group. Finally, to get a clear picture of the in vivo dynamics of D1 and D2 MSNs as animals perform this task, we recorded from channel rhodopsin tagged D1 or D2 MSNs. At present, we've isolated a population of 20 D1 MSNs and 42 D2 MSNs, and we've noted that ramping appears to be slightly more prominent in the D2 MSN population than the D1 population, although this is still a work in progress. Finally, looking at the population of neurons we recorded as a whole, we used principal components analysis to identify the prominent patterns of ramping in our ensembles, and we've noted that the interval spanning ramp that is 0 to 18 seconds, here PC1, accounts for much more of the variance than the shorter 6-second ramp. And we're interested in determining whether or not either of these activity profiles is more common amongst either population. In conclusion, time-related ramping is prominent across striatal ensembles, a process we attempted to describe with linear models. Additionally, D2 optical inhibition appears to robustly impair interval timing performance. Finally, DRD2 blockade impaired striatal ramping activity, a profile which appeared to be particularly prominent amongst our tagged putative D2 MSN population. And here are the citations. I'll be happy to discuss this with you during the Q&A session. Thank you.